find the first and last position of an element in a sorted array. So we're given a sorted array in ascending order, and we're giving also a target. And the goal is to return the first index of this target and the last index of that target. So basically the boundaries of that target. So if you go through this example, we have a target of 8, and we should return position 3, which is the start position, and position 4, which is the end position. Why 3? It's because it's 0 index. Yeah? So 0, 1, 2, and this is the third. And if it's not found, we should return -1 and -1. So for example here, we don't have 6 in our list, so we just return -1 or -1. Of course, if it's an empty array, you return also -1, -1. And note here, it says you must rewrite the algorithm in O log n. So intuitively, whenever you have a sorted array and you need to search for something, it's usually wise to use binary search. And here it makes it even explicit that you are forced to use binary search, because you can just make a linear search and do the same, but it would be very consuming, and we want to make it in O log n. So in that case, we would use the binary search. The challenge here is not that you just find the number, is that you want to find the boundaries. And to do that, we can think of it in that way. So I will just type here the input array, which is 5, 7, 7, 8, 8, and 10. And the target here is equal to 8. And here is the indices. And we can just simply think of it as two binary problems, two binary subproblems. So one binary problem, binary search problem, to find the left bound, meaning the first occurrence, and another binary problem to find the last bound, meaning the last occurrence. And how would you do that? Basically, at every stage you do binary search, yeah? And if you're looking for a left boundary, how do you know if this is the leftmost element? So leftmost, let's type it in a more clear font. So it's the leftmost element in two cases. Case 1, it is the first element in nums, or in the array that we have. So if it's the first at position 0, that means it's 100% the first one. The second case, the element before it, just before it, is not equal to target. And what does that mean? So assume here the target is 8, yeah? And the target is 8, and I come here, this is the 8 I found using the normal binary search. I check, is this the first element? No, it's not. Is the element before me equal to me, basically the same as target? No, then I'm sure this is the first one. And this is because it's a sorted array. So that's the two conditions we need to check to make sure it's the leftmost element. And of course, if we do that, then we just return the index. The other subproblem is the same, but we do it on the right side. So again, let's ask the same question here. How do you know it's the right most element? It's similar again. So you have two cases where it's the rightmost element. First case, it is the last element in nums. So if it's the last one, then we are guaranteed that this is the last occurrence. The second one is the same here. The element just after me, next, is not equal to target. And that's it. So we split the problem to two cases, left element and right, like left. So we split the problem into a binary search, basically on the leftmost element to find the index of the leftmost element, and to do the same with the rightmost element, and we give it the same nums array. Let's head to the code and see how it's done in action. So this is the signature. We receive nums and we receive target. What we do first is we define as I shown you here, we are here having a tree to get the left bound. Let me just make this a bit more, yeah, I think this is more clear. So we have a method, find bound, and this is basically a binary search, but with modification that I will show you now. And here we have the left bound. And again, we have the right bound and return both. That's it. And here we just have a safety condition in case it's not found on the left bound, so we are guaranteed that this element does not exist, so we return -1 or -1. Let's go to the trick part. So this is the whole thing. So here we have a found bounds, and basically the goal of the found bounds is to get these first leftmost element and the rightmost element that we specified. And to do that, this is a basic binary search. So you know how binary search works. We just have two indices, one left pointer and right pointer, and as long as the left pointer is less than or equal, then we keep carrying on. So at every stage you would have three possibilities. Let's go with the easy ones first. So one possibility is that the pivot that you're at is bigger. And if that's the case, then okay, it's not going to be on the right bound, it's going to be on the left bound. So you set it's going to be on the right side. So you just make the left start from here. Otherwise, that means that the element that at the pivot is bigger. And if it's bigger, that means we have to look on the right side. Yeah, so that's what we have. These are the two normal conditions that we have here. However, here, this is the third case. So assume now that I found the element. So I'm here and I found this 8. Okay. Now I want to check for the left bound. So assume now this is the left bound. So this method, as you see, it has a boolean because I don't want to write that twice. I just make a boolean here that says if it's the left bound I'm looking for or the right bound. Now let's start with the left bound. So if the left bound, as I said, we need to make sure for two cases. First is to know if this is the first element in the array, and if it's the first element, that means that the index m is basically 0. You don't need to have the less than, I just do it for safety. So m here is basically the index, that the middle point or the pivot, and if we check if the index of the pivot is 0, that means it's 100% the first one, so we return the index right away. Second case, we check the element just before me, and I do that, I just check the element just before the m. And again, if it's not equal to target, that means, for example, I'm here and I check here, okay, it's a 7, so I'm sure now that this is the first occurrence of the target 8. Then I return it. Otherwise, if that's not the case, then I know there exists a target at a lower index, meaning before me. So what do I do in that case? I narrow the problem down. So I make the right index to be exactly just before me. So assume it was here the pivot, I checked, okay, there's 1, 8 before me. So that means I'm not the first occurrence. What I do, I discard this part of the array and I just work on that part. And to do that, you just have the right pointer to point at this index just before the pivot, and that's what we do here. That's the case for the right bound. As I told you, I use the function for both. So I have, for example, when I have a right bound, I just pass false. Otherwise, it's true by default. So if it's a right bound, this is the case of a right bound, it's the same. So how do I know if this is the last occurrence of the target? Case 1, it's the last element. So if the m is equal to the length, the last index, so if it's here, then I know this is the last element and I don't need to look further. Otherwise, if the element I'm here and I check the one after me, if it's not equal, that means that I'm the last occurrence and I just return it. The other case is that if I'm, let's say, here, the pivot, and I check the one after me, okay, it's the same, that means I'm not the rightmost. What I do then, I discard this initial part of the array and I only search here. And that's what we do here. We just move the left to be at this position and we carry on repeating the same cycle. So if we go back to the code, like the initial function I have, that's what I did here. So I have the left bound, and you notice I don't pass a boolean here because I set this the default value. And I just make it more efficient by saying, okay, if the left bound would not find it, that means the element does not exist, so I don't even need to go through the right bound again. If it came here, that means, or it arrived at line 7, that means there is a right bound, or there is an element found. So I check it again, but this time I pass the value to be false, meaning that I'm looking for the rightmost element. And by the end, I return the indices I get from left and right. It's that simple. It just can be a bit, confusing in the beginning what you should do, but I found this to be the most optimal way and the easier way to understand the problem by just thinking about it in these conditions that I mentioned here. I hope you can read my handwriting. I'm working to improve it, but this sums it up. Let's think of time complexity. So it's a binary search, meaning that every step we discard half of the input, which means that it's log n. And you can think about it that we have here a log n and we have here a log n, so it's 2 log n, and you can discard the constant, so it's O of log n. Space complexity, it's O of 1 because the space does not grow with the input size because we don't store it. We just have our own variables to store the pointers. And what else? Yeah, that's the variables that we own. So it's O of 1 in terms of time space. And this works when you submit it. Everything is fine. I hope it was clear. And thanks for sticking there.